Hello everyone. In this video we're going to talk about the unit circle and how we can use the unit circle to help us evaluate our trig functions at many more angles than we could before. So our first exposure to our trigonometric functions was through our right triangle trigonometry. Right, so if we had a right triangle, so here's our 90-degree angle, this is our angle of interest that we'll often denote as theta, and then we can evaluate our 6 trigonometric functions using different ratios of the side lengths within this right triangle. So maybe we label the bottom of our triangle or the side adjacent to our angle theta as x, then the side opposite of our angle theta or the height of our right triangle we can call y, and then the hypotenuse by the Pythagorean theorem we know would be the square root of x squared plus y squared. But let's go ahead and simplify that quantity and just call it r for now. Well, in our right triangle definitions of our trigonometric functions, we saw that sine of our angle theta would give us the ratio of the opposite side length to our hypotenuse, or in terms of our labels here, that would look like y over r. Cosine of theta would give us the adjacent side of our right triangle divided by the hypotenuse of our right triangle, or in terms of our quantities as we have labeled them, that would look like x over r. Tangent of theta was opposite over adjacent, and for our setup here, opposite over adjacent would look like y over x. And of course we had our 3 other trig functions, secant, cosecant, and cotangent, but for now we're just going to focus on sine, cosine, and tangent. Alright, so I've gone ahead and drawn our right triangle and embedded it inside of our circle, but I'm going to modify this picture just a little bit here. And so technically this process could work no matter what the radius of our circle is, and we'll talk about that a bit more later on. But the unit circle is really special because it has a radius of 1. And we're going to see more and more advantages of using the unit circle pop out as we are working with the unit circle. And the first advantage we can see right away is, well, if we are on the unit circle, then the radius or these r values are all going to be equal to 1. And that's going to allow us to simplify our trigonometric functions. So sine of theta, instead of looking like y over r, is now going to look like y over 1, or just y. Similarly, cosine of theta will simplify to just x, but tangent of theta will still remain y over x. A couple other really important things to note about working with the unit circle here is, well, if we go over to our right triangle that we embedded, well, what we can notice is that this upper corner of our right triangle is landing on a point on our circle. So that means we can use these side lengths of our right triangle to help us find a point on our circle. Alright, so we set r equal to 1, and now if we want to find this x and y coordinate of this point on the edge of our circle, well, we know we just have to go over to the right x units and up y units, but that's just coming from the base and height of our right triangle. So what this observation is going to allow us to do is, instead of remembering these special triangles to help us evaluate our trigonometric functions, we can instead evaluate our trigonometric functions using known points along this special unit circle. And we're going to figure out a bunch of these points together here soon, and it's going to allow us to evaluate our trig functions at way more angles than we could before. So another very important observation that we need here that also motivates why we use the unit circle instead of a circle of another radius besides what we saw before is that, remember, our arc length formula that we talked about earlier said that our arc length s is equal to the radius of the circle multiplied by the angle extended by that arc length theta, where theta is measured in radians. But if we are on the unit circle where r is equal to 1, then our formula simplifies to s is equal to theta. So the arc length and the angle on the unit circle are essentially interchangeable and can be swapped out. And so what this arc length equals to angle observation allows us to do is, instead of thinking of our trig functions as functions of these angles within a right triangle, we can now start thinking of our trig functions as functions of these arc lengths traveling around our unit circle. Whether you want to think of the arc length or the angle, it doesn't really matter. We're getting to the same point. But the idea is this special angle or this special arc length on the unit circle are going to carry us to a single point, x comma y. And with those x and y coordinates, we can evaluate our trigonometric functions. So with our new unit circle approach to evaluating and working with our trigonometric functions, hopefully with a little bit of experience, we're going to start to realize that this is a more advantageous process to use, because now sine of our angle theta is just going to correspond to a y coordinate of some point on our circle. Cosine of our angle or arc length is going to correspond to the x coordinate attached to that point, and tangent of theta will be that ratio of the y coordinate to the x coordinate. And we can define our other trig functions in similar ways, just extending those natural definitions that we got from right triangle trig. So we're going to work together, use some of our special triangles and some symmetry and geometry arguments to find 16 key points around our unit circle. All right, so the first points we're going to find in our unit circle are going to be the known points in the first quadrant, and we're going to start there because in the first quadrant all our angles are between 0 and 90 degrees, and that's kind of where we're most comfortable with using our right triangle approach. So in our discussion of right triangle trigonometry, we talked about a couple of those special triangles, one of them being the 30, 60, 90 triangle. In our earlier video, when we were discussing this special triangle with those angles of 30, 60, and 90 degrees, we started with the triangle having a hypotenuse of 2. And what we ended up finding was that the height of our triangle was 1, and the base of our triangle was the square root of 3, or the side opposite of our 30-degree angle was 1, and the side opposite of our 60-degree angle was the square root of 3. And so we're going to be able to use this special triangle to help us find a special point on our unit circle. But we're going to have to make some modifications first, right? The idea is we want to eventually embed this triangle over into our circle. Well, when we were embedding that first triangle, we saw that the hypotenuse of the triangle corresponded to the radius of the circle. We want to keep that consistency going, but that's where our issue comes up. The hypotenuse of our triangle at the moment is a hypotenuse of 2, and so we need the hypotenuse to be of length 1 in order for it to fit in our unit circle. The good thing we know about similar triangles, and through similar triangles, we know that if we cut the hypotenuse in half or divide it by 2, we can divide all the other side lengths by 2. That'll keep all the angles preserved and give us a similar triangle. But this triangle will now fit inside of our unit circle. And so not everything is quite to scale here, but now if we were to bring this over and embed it into our unit circle over here, this hypotenuse of 1 would perfectly go from the center of our circle out to the end point on our circle. And what we know about that end point is that in order to get to it, we had to move square root of 3 over 2 units to the right and 1/2 units up. So that's giving us the x and y coordinates of that point on our unit circle. So we're going to be adding a lot more points and angles to our picture over here. So I'm not going to actually draw in the entire right triangle that helped us find this point. I'm just going to draw in the hypotenuse and label that hypotenuse with the corresponding angle. And so this was our 30-degree angle, right? We could visualize if we wanted to. This side length coming down here, meaning the x-axis, and then extending from the center to that point of intersection to really finish visualizing our right triangle. What we know is in order to get to this point on our circle from our special triangle, we had to go x units to the right, and that amount was square root of 3 over 2, and then y units up, and that was a value of 1/2. And so don't forget, when we're working with our unit circle, we said that our arc length s was equal to r times theta, but r was equal to 1. So our arc length s was equal to our angle theta, but this arc length formula only worked when theta was in radians. So we're probably most comfortable with degrees, so we're going to continue to label all of our angles with degrees, but we need to get used to using radians, so we're also going to convert all of our angles from degrees into radians. So let's go ahead and start with our 30-degree angle. Remember, if you want to convert an angle from degrees into radians, you just have to multiply by that special conversion factor of pi over 180. And if we take the time To simplify that fraction here, we end up with pi over 6. And so this is one of our first known points on our unit circle. Square root of 3 over 2, comma 1/2 is the point on our unit circle corresponding to an angle of 30 degrees, or in radians, an angle of pi over 6 radians. Now, if we want to find cosine of 30 degrees, we just have to remember cosine is equivalent to the x-coordinate of that endpoint on our unit circle. And so cosine of 30 degrees is going to spit out that single value of square root of 3 over 2. Sine of 30 degrees, or sine of pi over 6, we can now quickly read from the unit circle, will be that y-coordinate of 1/2. And well, tangent, we could just take the y-coordinate and divide it by that x-coordinate, or take sine over cosine. It's all the same. All right, I said that we were going to find 16 of these key points around the unit circle together, so 1 down, 15 to go. But don't worry, we're not going to have to do as much analysis for all the remaining 15 points. We'll be able to use lots of symmetry and geometry arguments to speed the rest of the finding the points up. And I forgot to mention this earlier, but I think now is a good time to do so. In the description below this video, you're going to find a link to a blank unit circle. I think it's a great idea to pause this video, print one of those blank unit circles out, and fill that unit circle in as we go through this process together. All right, so from our 30, 60, 90 triangle, we found this one point on our unit circle, square root of 3 over 2, comma 1/2. But we can also rotate this triangle around, flip it a bit, and find another key point on our unit circle, this time corresponding to our angle of 60 degrees. So when we're embedding these special triangles into our unit circle to have the triangles help us find these special endpoints, we're always kind of having the central angle be the angle of interest inside of our right triangle. Right, that's what we saw for our first angle, or first arc length of 30 degrees. And we want to get that same kind of setup going for our next special angle and endpoint corresponding to 60 degrees. So that means if we're going to try to visualize embedding our triangle, our 60-degree angle would have to be coming up from the x-axis, going up here to some point near the top of our circle, and then extending down. So it's going to look something like this if we were to kind of slide it in or out of our unit circle. Well, the nice thing here is we really just get to recycle some of the work we already have done. Don't need to do too much more analysis, right? We know that we want the hypotenuse of these right triangles in order to fit inside of our unit circle to be of length 1. Well, we already have our 60, 30, 90 triangle down here with a hypotenuse of 1. We just have to make sure we now label these mirrored and flipped sides correctly. So remember, the side opposite of our angle of 60 degrees is the square root of 3 over 2, and the side length adjacent to 60 degrees, or the side length opposite of 30 degrees, is 1/2. So now when we slide or embed our 60-degree triangle with a hypotenuse of 1 into our unit circle, we find that we end up at this point near the top of our unit circle where the x-coordinate is 1/2 and the y-coordinate is the square root of 3 over 2. All right, so this is our second point that we have found together on the unit circle. The point on the circle is 1/2 comma square root of 3 over 2, and the angle that gets us there was our 60-degree angle. But remember, we want to start working with radians here. So what is 60 degrees in terms of radians? Well, you can apply that conversion factor, or just remember 60 degrees is twice of 30 degrees. If 30 degrees is pi over 6, then twice that is going to be 2 pi over 6, or pi over 3. All right, so far so good. I think that's all we're going to get out of our 30, 60, 90-degree triangle, as long as we're staying in the first quadrant. But we have another special triangle that we talked about, so let's go ahead and see how that fits inside of our unit circle. All right, everyone, so now we're going to talk about how to fit our 45-degree special triangle into our unit circle and use that to find some more points along the outside of our unit circle corresponding to the angle of 45 degrees, or the similar angle or arc length in radians. And so one version of our special 45-degree triangle looks like this, where the base of the triangle and the height of the triangle are 1, and the hypotenuse is the square root of 2. Well, like our other triangles, we want the hypotenuse to be 1 in order for it to fit inside of our unit circle. So we're going to have to shrink or scale this triangle down. So if we divide all the side lengths by the square root of 2, then that'll make our hypotenuse equal to 1. Remember, the hypotenuse of these right triangles corresponds to that radius, and so we need the radius to be 1 if we actually want to embed it or fit it into our unit circle. All right, so now we know when our hypotenuse is 1, these side lengths are 1 over the square root of 2, but we want to rationalize these denominators. So remember, to rationalize a denominator with a single square root in the denominator, you just have to multiply the numerator and the denominator by that square root. So that'll give us the square root of 2 over the square root of 4, which simplifies to the square root of 2 over 2. So now in our unit circle, we can add a bit more information in. We know for this special 45-degree angle, we could fit a 45-degree right triangle in there with a hypotenuse of 1, and the base and the height of that right triangle would both be the same, the value being the square root of 2 over 2. All right, that's excellent. So now we know if we evaluate cosine or sine of 45 degrees, either way we get the x or the y coordinate being the same, and that's the square root of 2 over 2. But we want to start working with things in radians instead of degrees. So what is 45 degrees in radians? Don't forget about our conversion factor. Just multiply 45 by pi over 180, simplify that fraction, and we find our equivalent angle, but in radians, is pi over 4 radians. So remember, we can think about getting to this endpoint in multiple ways. Now that we're working with the unit circle, we can think about going up to our point by rotating our angle to a 45-degree angle, or we can get to our point by starting at this, call this the starting point on the unit circle, where it intersects the x-axis, and traveling an arc length of length pi over 4 to get us to that end point, or terminal point, as we'll call it, on our unit circle. So we've basically gotten all the information we are going to extract from those special triangles we discussed earlier, and those helped us find these 3 key points in the first quadrant. There's a couple points that we're going to find, well, not necessarily in this quadrant, but at the edge of this quadrant to finish it off, and then we're going to use geometry to fill in the rest of the circle. In the end, we're going to have 16 key points that we want to know and have memorized on this unit circle. All right, so there's a couple points that we kind of get for free on the unit circle, and that's the starting point where our circle intersects the x-axis. Remember, this is a unit circle of radius 1, so we know that y-coordinate is going to be 0, and the x-coordinate is going to be 1, and well, we always think of our angles as being like in standard position, or our arc lengths starting as if they were in standard position in this unit circle. So if we're kind of starting at this point 1, 0, we haven't done any rotation to get there, so that is going to correspond to an angle of 0 degrees or 0 radians. Right, and this is that first point that we would not really get or be able to work with if we were using our right triangle approach to our trigonometric functions. Right, in your right triangles, all your angles have to be strictly between 0 and 90 degrees. None of them could be 0 and none of them could be 90 degrees. So with our right triangle approach, we couldn't evaluate our trig functions, but now we're going to be able to with this extended definition. Our extended definition still works for our previous definition. We recover all those values, but now we're going to get so much more out of these functions. So now we know if we were to take cosine of 0 degrees or 0 radians, cosine takes the x-coordinate of that point on our unit circle, that's going to be 1. If we take sine of 0 degrees or sine of 0 radians, sine tells us what the y-coordinate of that point on the unit circle corresponding to our input angle or input arc length is. All right, we can make a very similar set of arguments for this point at the top of our unit circle. Right, that is our y-intercept, and so it's going to have x and y coordinates of 0 and 1. Remember, we're finding that y value of 1, knowing that we are on the unit circle where our radius is 1. And so now the question is, well, what is this angle that gets us from our starting position to the top of our circle? Well, that is definitely, just looking at the rotation we did here, a 90-degree angle. So our angle of 90 degrees is going to correspond to the top of our unit circle, or the point 0, 1. And if we write that in radians, that is going to be pi over 2 radians. So remember, we're working our way towards finding 16 key points on our unit circle. We're going to want to have those 16 key points memorized, as well as all the corresponding angles in both radians and degrees. And that's a lot of information to remember. It's definitely worth remembering, but there's some strategies that we can use to really help us remember all that information. And the first part of that strategy is really the first quadrant is the most important quadrant to remember inside of our unit circle. Once you have that first quadrant memorized, we're going to be able to use some kind of symmetries and geometries to recover or find all the other points that we need to have memorized.